Good afternoon, everyone. I would like to invite our next expert, Dr. Raghuvir Pisulankar sir, works as a professor at Goa College of Pharmacy, Panji. He will be taking the session on computational approach in drug discovery. Welcome, sir. Over to you.
Yeah, thank you. So, good afternoon, everyone. So, I'm going to be taking a session. Okay, next, our journey will be through use of computational tools for drug discovery. Okay, and uh, basically, tools that you can use on daily basis. You need not to buy, and so we'll look at some of these things now. Um, so just to brush up with the drug discovery, our traditional drug discovery basically refers to a process where we try to identify new therapeutic agents through experimental approaches. That means we will do synthesis, then we will do testing on, and then we'll see whether there is any outcome. Now, the problem associated with this particular type of traditional drug discovery, it's often time consuming. That means a lot of time. It takes long time. Okay, and resource intensive, meaning too much of material is utilized. Okay, uh, I'll give like example. I can tell you is, let's say you synthesize 100 compounds. Okay, and you do a QSR on that. Okay, you do synthesize 100 compounds, do as biology testing. Okay, and then try to correlate the SAR, that is structure activity, through a quantitative fashion. That means you make models which you can predict new activities. So now when you make changes, okay, those changes will tell you like what changes are enough, okay, to make the molecule more active. So this way you will end up with lesser synthesis rather than, let's say, synthesizing 1,000 compounds. Okay, you can synthesize only 100 dot points. Okay, so rational discovery basically employs computational tools. Okay, in the beginning and in the middle. Okay, to design the compounds at the start and to optimize them over a period of time, that will give better understanding of the drug interaction or your molecule interaction with the biology. Okay, so these tools make the drug discovery process cost efficient, okay, and faster. Okay, so like in places where drug discovery takes around 3 to 4 years to get one molecule into trials. Okay, computational tools will help you to get it within few months. Now, let us brief on what is called as the stages of drug discovery. Okay, first is the target identification, where you need to normally, as chemists, what we do is we will synthesize lot of chemical compounds. Okay, different heterocyclic cores, different diverse structures, new compounds. Okay, and then the question comes is what is the biology for these compounds. Okay, but in rational drug design, you first identify the target. That means where you want the biology to take place. So this will let you decide upon what type of target you are searching for. When you search for the target means when you inhibit that particular target or you activate that particular target, okay, what happens is you get a desired therapeutic response. Okay, that means the biology that you desire is available. Okay, so so that is basically target identification. That means searching for the biological target. Okay, that will give you the active. So, target identification, which will allow you to basically think of biology or give the desired action. Now, validation is the second terminology in target identification and validation. Validation means that target is of therapeutic importance. Now, let's say that you have, I can give you example like certain antibiotics. Okay, certain antibiotics work on only on their desired action is on microorganisms, okay, but not on humans. That is because the target or the protein on which they act are not available in the human system. Like for example, dihydrofolate reductase. Okay, now dihydrofolate reductase is an important enzyme in the microorganism which basically is required for the synthesis of folic acid. Now, if you inhibit that particular target, okay, synthesis of folic acid is stopped. But as far as the human is concerned, we have we consume folic acid directly, so we do not synthesize folic acid. Okay, so our folic acid resources are not affected, whereas the folic acid resources of the microorganism is affected. Okay, so that is validation means if you remove that particular protein, that organism will die. Okay, so that means that validation is successful. Next we go to what is called as hit identification. Now hit identification, when you do a screening, that means either you do an experimental screening or you do a biological screening, okay, high throughput screening. The compounds that show activity on the first instant, okay, that means first time the compounds that they show active are referred to as hits. Okay, so you will, and then you will have a cutoff. Okay, like as you can have activity in millimolar, micromolar, okay, nanomolar. Now depending upon the cutoff, you will retain all those compounds that show biological activity in a certain range, whereas you will sort of remove them from, you will remove the others. And second, so, so those molecules that basically show biological activity, okay, in the first instance are referred to as hits. Now, you cannot convert all the hits into your drug. So, what do you do is you start looking at molecules, okay, looking at the molecules, looking at their ADME profile, toxicity profile, okay, the synthetic feasibility, okay, and based on that you convert molecules from hit to lead, okay, which we refer to as lead optimization. Now lead optimization basically, as we do it, hit to lead basically involves identifying or shortlisting compounds, okay, based on lot of computational and theoretical study, computational and experimental studies. Okay, so lead will be the compounds basically that you happen to take into the into your clinical or animal studies. The molecules that you take for animal studies will be referred to as leads. Okay, so because you take only few compounds, one lead which you study normally, okay, and the other compound few leads, other second or tertiary leads are kept in the tertiary leads are kept as backup. Then comes the preclinical testing. Preclinical testing are uh, carried out on animals, okay, which resemble the closest biology, okay. Mostly you carry out on mice, guinea pig, rats. Very rarely it is carried out in monkeys and dogs. Okay, very rarely, but most of the studies are normally carried out in mice, Wistar rats, rabbits. Okay, depending upon the closeness of the biology. Okay, and basically what you do in preclinical testing, you basically see whether there is any toxicity of any sort which these compounds exhibit, because these compounds are non-natural synthetic compounds. They can cause harm to the human tissue or tissue as such. So before going into human trials, which are called as clinical trials, we test them on animals. So we use animals as guinea pigs, or we use animals for a safety purpose, okay, to see whether any harm is caused. If no harm is caused in the animal trials, okay, then we take these compounds at a substantially lower dose in clinical trials. Now, if the molecule happens to fail in the clinical trial, then there is a lot of losses, okay, occurring right from for all the experiments that are carried out, right from target validation to lead optimization. The expenses or the chemicals that are utilized, the time that is utilized, the money that is utilized, all goes in vain if the molecule fails at the clinical trials. Okay, so then we have the regulatory approval, that is the FDA gives a, green signal, okay, to proceed ahead. After which you move ahead with the higher trials. In clinical trials, there are four levels: phase one, phase two, phase three, phase four. Phase four, okay. Phase four is basically referred to as marketing surveillance, okay, wherein the molecule, wherein the drug candidate is released to the market, okay, and during which surveillance or monitoring is close kept to figure out whether the molecule is causing any disturbance, okay. Like once upon a time, there were molecules like celecoxib, valdecoxib, rofecoxib, which basically came into the market, okay, as anti-inflammatory agents or painkillers, so to say, okay. But except for celecoxib, rofecoxib and valdecoxib had to be withdrawn because they was causing cardiac related problems, heart related problems. So computational chemistry basically has revolutionized the process of drug discovery. It basically helps by reducing the time, okay, and the cost which is associated with finding, optimizing, okay. Um, So the cost of 3 years is reduced to something like 6 to 9 months to get the molecules into preclinical trial. So you can understand the cost that goes over 3 years. It is shortened out. Like you may not synthesize all the compounds, okay, but a few compounds that are promising with activity in computer world. Now, coming to molecular modeling or molecular mechanics. Okay, the study of molecules and its motions, the movements, okay, flexibility in the molecules, okay, is referred basically by a term called as molecular modeling. So here we try to study the shape of the molecule, okay, and the energetics of the molecule related to the shapes, okay, and we try to see which molecules, which shapes are better, okay, and their interaction with other macromolecules. That means interactions of small molecules with biological compounds. Okay, so we can understand the molecular structure, we can understand its uh, electronic homo lumo energy gaps, we can understand its electrostatic potential, we can understand their dielectric constant, dipole moment, solubility. Lot of parameters, okay, can be understood and predicted. Lot of properties can be understood, the molecular reactivity can be understood, okay, and which can help in the process of drug design and discovery. Okay, so molecular mechanics is a computational approach that used to model and predict the behavior of molecules. Okay, now these molecules could be small organic molecules, it could be proteins, it could be DNA. Okay, now when we talk about molecular mechanics, okay, one concept that surfaces, okay, comes to our mind is force field. Okay, now force field is basically a mathematical framework or mathematical equation, okay, of molecular mechanics that basically helps to calculate, okay, or compute the potential energy of the molecular system. Okay, so we can compute, as I talked about in the starting, that molecular mechanics basically deals with the uh, structures of the molecules and the structures of the molecules and the energy structures or shapes. Okay, rather structures are different, okay, shapes I would say, then and the energy associated with the shapes and transformation of one shape to another, which is very critical in the world of chemistry. Okay, so we try to design what is called as flexible molecules, we try to design rigid molecules. Okay, so this helps us through a force field, which helps to calculate basically the potential energy or simply the energy of the molecule. This equation is given in the form this way, you can see it here. Okay, basically the potential energy is the sum of energy because of the bonds, the angles, the torsions, the charges in the molecule, and the distance between the atoms. Okay, so okay, so I'm not discussing much on the force field here. Okay, so force field basically what it will do is uh, it calculates energy. So now whenever there is a bond, if you look at a structure, okay, so if you look at the structure, if you look at the structure of any molecule, okay, we can decompose the structure into atoms which are connected by bonds. Okay, two atoms are connected by bonds, so that is the sequence. Then the three atoms in the structure are connected by an angle. Okay, and four atoms are connected by a torsion. So when two atoms, come close together or they move away from each other, they exhibit force. They exhibit force, okay, which can be computed in terms of energy, okay, given by this particular set of equation. This term, which is called as KB r minus r zero the whole square. Okay, where So first term in this equation is with regards to bond. Second term is with angle. Third term is with respect to torsion, and fourth and fifth term is with respect to charge and van der Waal interaction. So moving ahead, okay, we have angle term. Okay, now this angle term basically talks when three atoms, okay, when we have three atoms, atom 1 connected to atom 2, which is further connected to atom 3. Now atom 1 and atom 3 interact by a scissor action. Okay, like if you look at a scissor, okay, so with the scissor action, the atoms 1 and 3, they come together and they move apart. And while doing so, okay, and while doing so, there is changes in energy. Okay, now these changes in energy can be captured by this equation, which is referred to as uh, k theta, theta minus theta 0, the whole square. Okay, now theta is the angle, okay, between three atoms, and theta 0 is the angle at equilibrium. The next we have what is called as torsion angle. Now the torsion angle is the 1-4 relationship of atoms. Okay. Now when atoms are connected by by one and two atom is connected by uh, a bond. 1, 2, 3 is connected by angle, and 1, 2, 3, 4 is connected by a torsion. Okay, so the you must have heard about torsion angle, like when we have a, you know, a butane which is cis. We have a butane which is basically staggered or eclipsed. Okay, the first and the fourth atom, they are in close contact, or they are far away from each other. Okay, so we can compute torsion in this particular equation. Now, when next we have is what is called as charges. Okay. Now, charges, when they are of same type, they repel each other. That causes the energy to spike. Okay. And if charges are of opposite nature, that means plus minus, they tend to attract. Okay. And attraction causes the fall in energy. That means increase in stability. Remember, in terms of force field, when the energy goes higher, then we say that the molecule is less stable or highly energetic. Whereas when the energy goes down, okay, then we say that the molecules are stable, okay, and with low energy conformations. Now let us come to our main topic, that is structure based drug design. Okay, now we have in drug design or rational drug design, which I told you is the use of computers to basically design molecules, okay, that shortens the time interval for the molecule to reach into the clinical trial and simultaneously save on the cost of the chemicals that are utilized. Now, rational drug design is divided into two types. One is called as the structure based drug design, okay, which takes structure here refers to the three dimensional structure of the biological target, which is an enzyme or a receptor. Okay, to which basically the molecule binds, okay, and exhibits a therapeutic action. So when a molecule binds a receptor, okay, it binds to the receptor as an agonist or an antagonist. The agonist is a substance which is supposed to bind to the receptor and produce a positive biological action. An antagonist is a chemical substance that refers to binds to the active site on the receptor and prevents the receptor from changing its shape, which is necessary for the biological action. Okay, so agonist will cause the receptor to change its shape and execute a biological action, whereas an antagonist will bind to the receptor and do no such thing of twisting the receptor or activating the receptor. Now, enzymes are proteins, okay, or therapeutic targets in our study, which convert substrate into product. Okay, now the substrate conversion to product, okay, either it could be a beneficial action or it could be a harmful action. Okay, like for example, in acetylcholine esterase, which is an enzyme, converts uh, acetylcholine or breaks it down acetylcholine, okay, hydrolyzes it out. Now, acetylcholine is a neurotransmitter. That means it is required for the functioning of the body, okay, the brain and the body, the muscles, the nerves. Okay, you destroy that chemical, the body starts resisting functions. Now, too much of it causes too much of acetylcholine may cause paralysis or uh, it can lead into tremors. Okay, so both ways, either it is a good or a bad signal. So if you want to save acetylcholine for biological activity, then you design molecules which will inhibit the acetylcholine esterase, okay, and prevents it breakdown. Okay. Okay, I had a video here to show. But Okay. So basically, what you see here is the start of the topic, that is molecular docking. Okay, and how it works is molecular docking is basically placing the small molecule in the binding site or the active site cavity of the protein. Okay, and we basically do that for inhibitors. Okay, so here you can see two color molecules. Okay, this is the active site or this is the binding site. Okay, you can see one structure, small molecule structure, which is different color. So one is a binding structure and other is the new compound. Okay, so this helps us in the uh, designing, okay, finding the affinity. So docking is basically a computational approach which helps us to predict the interaction between the small molecule that we design, okay, and the target macromolecule, which is basically the enzyme, okay, and whether it is going to else. We can understand the binding affinity, means the stickiness, okay, the energy required to break the complex, or energy required for the molecule to bind to the protein. Orientation, as in how the ligand basically binds, what shape it takes, okay, and therefore we can take a decision, okay, whether the ligand has any affinity to the target or not. The next we look into the concept of types of docking. Now, docking, what we know from online tools that are available, we use a software called as Autodock Vina, okay, which is a free resource to carry out docking. Uh, so there are three approaches. One is called as a rigid docking. So here you can see, I have put up a graph, okay, of rigid docking versus semi-flexible docking versus flexible docking. So you can see particularly on this graph, okay, there is a speed versus accuracy. Now, rigid docking, the protein and the receptor are treated as solid compounds. Okay, that means they do not change their shapes. Okay, and when structures do not change their shapes, the interaction can be found very fast. Okay, the interactions can be found out very fast. Therefore, the speed is good, but accuracy is not good, basically because when we look at solid interactions, okay, we do not consider what is called as the flexibility. Okay, the molecules may bind to each other but they may not have shape, you know, like jigsaw puzzle type of shape, same shape. So because of which the accuracy is a question. So what tools that we use is normally semi-flexible docking, wherein the protein is held rigid. These are the tools that are available online and downloaded. While the ligand is allowed to move, change conformation, change shape in the binding site. अच्छा. Now, when we do protein molecular docking, we have to prepare the protein, okay, and we have to prepare the ligand for docking, okay. Now, in protein, normally what happens, we make the crystal structure which is available is protein database, from where we can download the structure of the protein, okay, for docking studies. Now, the crystal structure, that is the three-dimensional structure of the protein, normally has water molecules and some other chemical entities, okay, non-essential structures bound to that, which we do not require. Okay, so we have to remove them. Then sometimes what happens is the protein structures that are available, they do not have hydrogen atoms, so we need to add the hydrogen atoms. Then the partial charges, formal charges, they are not available. Structures are broken down slightly. Okay, we need to repair. So all this forms the part of the protein preparation. So once the protein is prepared, we can go in for the docking. Now, before starting actual docking, we need to know the binding site. Okay, the binding site is the region where the docking basically takes place. Okay, so that is the active site or the site of catalytic site, substrate site. Okay, there are different nomenclatures to this. So we need to define the binding site. Now, if we do not define the binding site, the software will not know where to dock the compounds. Okay, so it may dock at any other place in the protein structure. So avoid that. We do what is called as a binding site definition or a location in the protein. Okay, we can see in this case here or in this case here. Okay, you can see that that is the binding site groove. Okay, where your molecule will tend to bind. So what you can see here, okay, is the ligand. This is a drug called as niraparib, okay, which binds to a protein. Okay, you can see this is the particular file, okay, or the structure which is called as the PDBQT format, okay, for this particular structure, which is used for docking purpose. It is generated from this smile. This structure here, what you can see, is called as smiles. Smiles stands for small molecule input line entry system. It is a chemical structure representation format in a straight line. Okay, it's a one line representation of a chemical structure which can be converted into the three dimensions. Okay, then we have what is called as scoring functions. Okay, scoring functions are like evaluations or like tests. So scoring function is like test, okay, as evaluation or giving marks. Like for example, if you answer an exam, okay, and if, how do you know it is a correct answers? There is evaluation test for it. So let's say you are answering an exam, okay, and there are no marks to it. So that means you can't evaluate. You don't know whether the answers are correct or wrong. But if you do evaluation, then you can figure out whether the answers are right or wrong. So similarly, scoring functions helps us to understand whether the docking performed is correct or wrong. So there are two types of scoring functions. One is called as the empirical. Okay, I will not go into the details. And second is known as the knowledge based. So basically, what we need to know when we do docking is whether the binding interaction is correct, okay, and the docking's binding energy or binding affinity is good enough. The next we do what is called as docking validation. Before we start the actual docking process, we do what is called as docking validation. Now, docking validation is a process in which we check the docking procedure. You can see here two structures, okay, one in lavender and one in rust color. Okay, the turquoise color happens to be the amino acid. Now we check whether the color, rust color and the turquoise color both bind, not turquoise, sorry, cyan color basically bind to the receptor pocket. So this helps us to validate the procedure. Okay. Okay. So I'll show you about the tool. Let me try to see if I can share it through the screen. Is my complete screen visible? Is the screen visible?
Sir, wait a minute, sir.
Is my screen
Okay, sir.
visible?
Now your screen is visible. Yes, yes. Now your screen is visible.
Okay. Yeah, okay. So now I will take you to a demonstration process. Okay. You go first, as I told you, we use a docking tool. Now, docking tool as Swiss Dock is freely available. Okay. And it uses Autodock Vina. Okay. So here you can see Autodock Vina has been highlighted. Okay. Now there are two different parts to it. Okay. You can see here. So there are five pointers or five things that needs to be done. Okay. First is you need to submit a ligand. Okay. Now, okay. So the ligand can be submitted, okay, as a smile. That means a single molecule input line entry system, or you can upload a structure if you have it, or you can sketch the molecule using the Marvin JS tool. Okay, so you can sketch the structure like this. Just randomly drawing some structure. Okay, so you can do the structure, draw the structure like this. You can prepare the structure, the red icon here. Once the structure is prepared, you get a green check mark. You reset it. Okay, you can put another structure. Now, as I said, if you know your compound, you can draw the compound here, whatever the structure you have designed. Okay, you can draw it here. Or you want to check some known compounds, then you can go to the website called as PubChem. Okay, and you can look in for some structures. Like I'll look for donepezil. So I can copy the smiles from donepezil from here. Okay, you can see smiles, and I'm copying the smiles from here and I'm pasting it here. Now, when I paste it with some error, you can see there's a problem. But when I paste it with correctly, error you see that something goes wrong here. But when you do that correction, extra space removal, you see that the ligand appears in this scene. You can hide the sketcher if you want, or you can change the structure. Okay, you can make some modifications to the structure if you want, and then you can prepare the ligand. This way you can prepare either your standard compound or your designed compound one at a time. So once you see there is a green icon, that means the compound has been prepared. पेपर मेरे को दिक्कत है अरे तेरी चॉकलेट की बात कर रहा हूँ then we need to submit a target that we want to dock. Okay, now this has to be done as I told you in the beginning of the slides. I've shown you that we need to know the target where we want to carry out the docking. Okay, so if we did not know the target, we need to do some part of literature search before we go into docking studies. Okay, now here for example purpose, I have taken donepezil, which basically binds to acetylcholine esterase. So I can search for the protein on this website rcsv.org. Okay, and I can look for acetylcholine esterase. I can search that with quotes or without quotes. So here you can see crystal structures available. Okay. Now since I know one of the crystal structures has got donepezil, juice लाया है ना juice. juice लाया है. So if you type donepezil, you can see human structures available, crystal structure of recombinant. Okay. Here you can see 7E3H structure, which is the structure of human acetylcholine complex with donepezil. This structure we will use for our docking studies. Those who have got laptops with them, please you can work with me along with. So I will take this particular structure. Okay. I will load it into the system. As you see that the moment the structure was uploaded, code was uploaded to the uh, web server, it immediately loaded the other parts of the module till when it was not there. Okay, nothing happened. Now what we'll do is you can see the protein here. Okay, there are two chains. We will fix that problem first. We will study the analysis. We'll study the docking only in one chain. And if we have any heteroatoms associated with that, we will keep, but we don't have any. Okay, heteroatoms that are, if we have something called as cofactors and all in certain proteins, then we will have to keep them during docking. Okay, but normally substrates and products we will remove it from the docking procedure. So next, what we will do is we will. So there is nothing to keep in the hetero. Everything is fine. So you can see that the prepare target has got highlighted. So we will prepare the protein for our analysis. Okay. Now you see here that we have a box. Okay, and we have the protein with us, but we don't know where to put the box. Okay, so in such cases we may put the box randomly or create a big box like this. Okay, so what you can see, we have created a big box around the protein. Okay, and such that the whole protein is engulfed by the box. Okay, we can see this here. So you can see here that I've tried to get the box at the center exactly of the protein, and the full protein is under the box. Okay, this is called as a blind dock approach, where you take the entire protein into the binding scenario. Okay, so I can increase 40 is the max. Okay, I can have it like 45. This will engraft the entire protein. You see, the entire protein is inside. Okay, I can keep the entire protein inside here like this. So this way I can now perform. I have, this is called as open docking. I can select the exhaustiveness to a very high number like 64 and very low number like 1. I will set it to a optimally good number like 4. Then I will say check parameters. So what it will do is the software module server will check whether the ligand is in correct conformation, the protein is optimized, okay, and the parameters are set correctly. Once we have this in place, then okay, you can see that the box is too big and it is shouting for the bigness of the box. Okay, so we'll shorten this to 40 and see if there is accepting it. Basically, what is happening is the search algorithm gets bigger and bigger. Still the box size is exceeding. Okay, so we can set it to 35. Let's see if that is getting accepted. Okay, so with the 30 box size, you can see that the docking has got accepted and the box is quite big. Okay, now we will carry on the docking procedure. Remember, this is a open blind dock. We don't know whether ligand should bind. You can put a name for this docking. Let's say we call it blind dock. Okay, and if you want, you can share your email address and then close the browser. It will download. Once the calculations are completed, you will get a notification and you can open the browser page. So I will start this docking procedure. So you can see here the parameters, submission date, name of the docking, ligand, target, box size, box center. Okay, everything is come. You can either bookmark this or wait for the calculation to take over. Okay, what I will do is, meanwhile, I will start another Swiss dock.
मेरे को उठा के लाने के डब्बा निकल सामने पड़ा है निकल नहीं रहा इससे इसे तुम इसको उल्टा लगने के लिए नहीं
So now we will restart docking again with same donor bezel, but this time what we will do is we will do a targeted approach. So we will prepare the ligand. We'll submit as protein code. Okay, then when we submit the protein code, what we'll do is we'll select the chain and we will try to search for the ligand in this binding site. Okay, so this is our ligand. So you can see here, you can see the ligand here. Okay, can see the ligand here. Okay, now what I will do is I will center the box onto the central atom of this protein ligand. So I will try to put the box around the ligand. So you can see now the box is around the ligand. Okay, exactly boxes around the ligand. I can shrink the boxes required. Remember the other box we had taken was 13. We can reduce this to 15. Okay, and that is enough space for the ligand to bind. You can see it's a perfect shape. Then what you can see is the search center. Now the search center in the earlier case was minus 56, minus 28 and minus 29. In our case, the search center comes to as minus 44, 38 and minus 31. Okay, you need to keep this in mind. You need to write it down somewhere, these numbers. Okay, before you proceed with the processing of the. So now when we are processing, coming back from 3 to 2, you're coming backward, we're looping it. Okay, we have selected the chain, but again we'll have to hide the target or the therapeutic bank to none. Okay, so all your settings are same reserved, settings are not affected, your binding position is not affected. What is getting affected is your prepare target. So with this you can prepare the target. You can see the target is prepared, the ligand is prepared. Okay, and we have defined a box which is different from that earlier one. I've set the thing to 4 and set the parameters. Difference between the earlier method and this method is in the earlier method I'm causing the entire protein. The entire protein is my search space, whereas in this particular only the binding site is my search space. So I will call this as active dock. That means I'm carrying out the docking in the active site of the receptor pocket. I will start the docking cycle. You can see the statistics here. Okay, it estimated to take around 49 seconds. This one is already completed. Now, when you are running out this exercise, okay, you need to use these references to pub in your research paper or in your research thesis to acknowledge the tools that you are using while conducting your studies. Okay, so you can see the results. Okay, you can see that the docking scores are available here. Okay, and the binding site. What I will do is I will download it as a zip folder and I can watch it using a software tool called as SpyMall, which is again freely available. Okay, now this job is, you can see this docking is also completed. Okay, and you can see the results are okay. Docking scores are different compared to the bind log. Now what I will do is I will use a tool called as SpyMall. It's a Python interface for molecular graphics. Okay, which will help. Even I will download these results. Okay, these results will get downloaded as active doc. So I have PyMol with me. Let us come to the download folder. You can see in the download folder I have got an active doc folder, okay, which has got the doc pdb, okay, it has got the system pdb, the parameters, modified pdb, everything is available, okay, even in the blind doc same stuff is there, okay. Now what we will do is we will get pdb, that is, okay, and we get chain a, okay. You can see that the ligand is there and there are some red dots. What you can see, they are water molecules. I can remove the water molecules. Say, remove waters. Okay, I will center visible. I'll center this. Set the background to bit white. Looks good. Okay, hide the card ribbon. Okay, and show the surface. Generating vacuum electrostatics, potent contacts, and it create a surface for me. Okay, you can see the ligand in the binding site. I will decrease the transparency on the surface to around 60%, so you can see the ligand. I will select the ligand and I will zoom on the active selection. So you can see the ligand here in the binding site. Okay, now what I will do is I will get the solutions, okay, from each of the folders that I've done. Okay, so I will get a Veena doc PDB from the blind doc. Okay, you can see it has docked at the same position. Okay, but with some discrepancy. Then you can see it has got solution, so you can check the solution. So it is even docked at some other binding site. Can you see here? There's another binding site explode here. Okay, which was not visible, but you can see that that is a shape complementarity between the ligand and the binding site. However, this is not our solution. A solution happens to be in this binding site, and unfortunately it has not come out. So blind docking has partially worked and partially failed, but you can see that it is attaining some different shapes which definitely have a binding affinity, okay, but not that great. Now let us try to look at a active site blind docking. So I just label it as active dock, okay, and then I will hide the Okay, so you can see that the active dock solution partially resembles the uh, binding site docking image. You can see these are the different conformation it creates over the period of time. Okay, so the first solution happens to be the most closest to be in the picture. Okay, so this way, of course, if I set a charge on it, then the docking scores will definitely change. Okay, now the next step for us to do is what is called as uh, can we take a 5 minutes break here? Then I'll go into the next session, that is uh,
Yes, sir, you can
excuse
take a
me.
break.
Yeah, okay.
Yes, yes, sir. Hello? Hello? Hello, sir. Hello, sir. Am I audible?
Okay, so I believe my screen is visible. Okay, and so we can look from here that docking. Okay, this procedure is validation, where we confirm that the uh, docking or the binding conformation or the binding pose of the ligand, okay, in crystal form and in the dog form are almost the same. So with that, we can proceed with docking any other ligand that we have designed, okay, in a laboratory to carry out the docking in the same manner. Okay, so what is the same manner? We'll go back to docking. We will go back to docking. Okay, we can use the, okay, we can start all over. We can submit the inhibitor. Okay, then the protein PDBQT we can choose from the one which we have already completed. Okay, so we can go to the dock, we can go active, and we can use the uh, system PDBQT which is already been docked. We can prepare the target, put in the same conformation and space parameters, and we can submit the docking. Okay, so this way we can run for all our ligands. Okay, now next I will talk about what is called as the binding site interactions. Okay, which You can see the binding site interactions here. Okay, so binding site analysis basically after docking. Okay, after we do docking all here, then we can do what is called as binding site interaction analysis, which basically helps us to understand the interactions at work. That means what interactions are taking place, what are important interactions. Okay, what are the interactions now? There are hydrophobic interactions. Hydrophobic interactions are Hydrophobic interactions are the interactions of aromatic amino acids with the aromatic part of the inhibitor or the ligand. Hydrogen bond interactions involve electronegative atoms like oxygen, nitrogen, okay, which share a hydrogen atom amongst the two. One, it is covalently bonded, and other, it is having electron pair interaction. Then we can have what is called as pi-pi stacking. Now, pi-pi stacking is a interaction in which two aromatic rings, okay, one electron rich, one electron poor, stack onto itself. Stack means place themselves one upon the other. And then we have what is called as cation pi interaction. A cation is basically a positive charge in the ligand, whereas pi is basically the electron crowd on aromatic amino acids. So when such a cation interacts with a aromatic amino acid, such an interaction is said to be a cation pi interaction. Then, of course, last we have what is called as the halogen bond. So, halogen like fluorine or chlorine also can form a bond, okay, like hydrogen bond with electronegative atoms in the vicinity. Such are referred to as halogen bonds. Okay, now we'll take you to the okay, so I will take you to a process of understanding binding site interactions. The tool that we use for this is called as PLIP, which stands for Protein Ligand Interaction Profiler. Okay, now how this basically works is uh, you can either choose a file, okay, or you can directly access a PDB code. So we'll try to access the PDB code method first. Okay, so you can see binding site interactions here. You can download it in visual format, which is the PSE format, it gets downloaded. Or for the time being, you can also look into this particular molecular viewer and try to understand the binding site interaction. You can see here now what was frozen is zooming in. So I've zoomed in a bit. So here you can see the legends of uh, the protein ligand water, okay, and other interactions. Now the interactions which are not visible, you can see that they're not highlighted or they are somewhat in gray color, whereas the interactions which are available and visible, you can see that they're in deep color or dark color. Okay, so let us start. So you can see that the protein is in turquoise format. Okay, ligand is in rust color. Then you can see the label on the amino acids, which is clear. Okay, And now let us look at the interaction. Now these gray bonds that you can see, they are all hydrogen, sorry, they are hydrophobic regions, whereas this, okay, you can see a pi stacking here. You can see a pi stacking here, which is between the tyrosine ring of the protein and the indane ring here, the five-membered pentasite, five-membered or five-membered ring system. That's your cyclopentanone. Okay, here you can also see another stacking interaction between the tryptophan ring here. Can you see the phenyl ring of the tryptophan with the phenyl ring, diphenyl methoxy ring of the donepezil structure? Okay, so this is one way of evaluating. Second way, as I told you, you can download these interactions, okay, in a PSC format, okay, which I've already done. Okay, and I will load it here into the PyMol interface. You can see that PSC is downloaded here. Okay, so here you can see the same interactions much more clearly. Okay, you can label these amino acids by selecting them, okay, and say label 3 amino acid residues. Now the labels are not that clear, so what you could do is you could go to settings, labels, size, and come to write 24. You can see that the size of the label has grown. Okay, next what you could do is you can click here and press Ctrl and mouse, and you can drag the label outside so it is in the visibility range. Okay, so this way you can get the label outside so they become visible during your study rather than remaining hidden like this way, so you can get them out. Okay, probably if they're not too many. Okay, and this way you can add a little bit of graphics, like from structure you can say show, uh, from structure you can say show generate surface. See that the surface will get created around this binding site. Okay, you can see the surface. You can decrease the, through settings you can come down to the surface transparency like around 80-60%. Okay, so here you can see the interactions. Okay, see the interactions here. I'll select the ligand. Okay, okay, so here you can see the interactions at play. Okay, you can remove the graphics a little bit. If you want, you can append the graphics to get a better view. Okay, and then you can capture images. Okay, save images from the file section. Okay, export as image, and then you can use this in your dissertation or in your publication. So any questions so far? Any questions? So that was about docking and binding site interaction. I will take you to the next topic, that is ADMET, which is another critical thing when you do drug discovery. There are several tools of conducting ADMET. I'll show it a couple of two to you. Okay. So before we move on, any questions pertaining to what is docking? What is the importance of docking? Yes. Hello. Any questions? students would like to ask any questions? Hello. So if no questions, I will proceed with the next part. Okay, so we will look at ADME. ADME is another critical thing when it comes to design and discovery. Okay, so there are three tools available on the website. One is referred to as the Swiss ADME, which helps you to calculate the physico-chemical properties. Okay, and it also helps you to calculate other things like blood-brain barrier. Okay, then metabolism. Okay, excretion. So I will take you through all these softwares one by one. Okay, so first we will look at Swiss ADME. Okay, then there is one easy tool which is called as Property Explorer, one of the very easiest tools. Okay, this tool is available for download from openmolecules.org. Okay, and when you type in the name of the compound here, okay, and or you draw the structure, then it helps you understand certain values like toxicity risk assessment is done, so you can understand whether the molecule is teratogenic, mutagenic, irritant, or having effects on the reproduction. Okay, you can understand its physico-chemical potentials like log P, solubility, molecular weight, topological, polar surface area, drug likeliness, and drug score. So if the drug likeliness score and the drug score are less or in the red zone, okay, then you need to modify your chemical structure so that the properties can change. Okay, so I will show this demonstration. Okay, so first I will take you to openmolecules.org, which is the most simplest one. Okay, so from here you can download the Property Explorer, which is called as the Property Explorer app. You download it, it's Java based. Okay, so to run, you can download it onto your server, or you can download it onto your laptops or computer. Okay, and it operates very easily. You double click on the Windows Compute icon and it runs on other machines. Okay, so I'm launching it on my laptop. You can see it is launched here. Okay, it uses a command line interface when it comes to other operating systems, but Windows you can just double click, it will run. Now you can type in any molecule structure here, or like for example, if I copy the donor basil smiles. Yeah, I can paste the smiles here and execute them. So you can see that the donepezil is available as a structure. Now what you can see with regards to, they're all green icons. Okay, mutagenicity clean, tumorigenicity clean, irritancy clean, reproductive effect none. Then you can look at the log P is good, solubility good, average molecular weight excellent, total polar surface area, high drug likeness, and average drug score. So this becomes a ideal molecule which is available in the market. If I type here valdecoxib, the molecule that has been withdrawn, this is the molecule that has been withdrawn from the market. Okay, very simple molecule but yet causing trouble. So I can paste it here. So you can see here valdecoxib. Now, if you look at this molecule, many of these properties are smooth. Okay, but the property that is not available here is the HERG. Okay, which is causing the change in the uh, cardiac rhythm. Okay, that property is not reflected. So as I told you, this is a very primary tool. You can see the molecules go. Okay. Next, we will look at a software called as, from the same website of Swiss Doc, we will go to what is called as Swiss ADME. Okay. So Swiss ADME helps us to understand the properties of molecules. Okay. Now, similar like to docking, you can either draw the compound of your choice. Okay, if you know the structure of the compound that you have designed, you can draw them, or you can paste the smile of the compound. Okay, like in this case, you can see the structure. If I paste the smiles here, okay, you can see the smiles getting pasted here, and I can push it into the ligand here. Then I will run the smile, and you can see the process has got activated. So you can see now here the different properties, okay, that are available. You can see the physicochemical properties like weight, heavy atoms, rotatable bonds, donors, acceptors, okay. Everything is available on this prediction model. You can look at this, what is called as your radial graph. Okay, in this radial graph, there are around six properties plotted out. One is lipophilicity, size, insolubility, insaturation, flexibility. You can see with regards to insaturation, the molecule is outside the limit. Okay, the fraction of sp3 atoms. Okay, unsaturation. Rest are all in the red zone, which is basically a acceptable region. Then you can look at other properties like water solubility calculated here. Okay, you can look at the pharmacokinetics, that means how the molecule undergoes or tunnels through the body. You can see it has got a good GI absorption. poor blood-brain penetration. Okay, then as far as uh, metabolism is concerned, it does not inhibit certain isoforms of cytochrome P450, whereas it does inhibit 3,4-A and 1,2-C. Okay, then Lipinski rule, Weber's, everything is available here. Okay, so this way you can use these properties to understand the chemistry of the molecule, okay, and how the molecule is treated inside the body. The next we will look at another server. Okay, another server is referred to as PKCSM. Okay, PK stands for pharmacokinetics. Okay, you can download the theory behind this. You can read the theory from this particular section. So, what is the theory I'm talking about? Is what are the different properties that are calculated by the PKCSM web server. Okay, so K permeability, intestinal absorption, then what is the model, like what is the model it is designed, and how do you interpret it. Then you have water solubility. Okay, then you can look at different absorption parameters like the glycoprotein 1 2 inhibition. Then what is the volume of distribution, means how the molecule is distributed entire body, whether it is crossing the blood brain barrier or whether it is crossing the CNS barrier. Okay, and how to interpret these results. Then whether it is a inhibitor, that means if it will block the metabolism of other substances while it is administered, or will it get metabolized. Okay, there are two aspects, whether it metabolizes or whether it gets metabolized. So both questions are answered. Okay, then about its total clearance, that means whether the molecule is removed from the bloodstream eventually or has got some toxic potentials. Then, when it comes to toxicity, there are different prediction modules like the AIMS toxicity, Minnow toxicity, pyriformis toxicity, the LD50 dose, okay, the hepatotoxicity, skin sensitivity. So, a plethora of toxicity tests are available, okay, which will help you to understand whether the molecule that we have designed is good or bad, okay. Because if it is bad, you can definitely make some alterations to make it towards good, okay, by studying. Whether it is undergoing skin sensitization. So, all these properties can be studied, okay. So, you can download this PDF and take your time to read it. Meanwhile, what we'll do is we can go through this prediction module. So, you can provide your smile here, okay, or upload a set of smiles in a text format. So simultaneously you can do multiple structures in this scenario. Now you can either only find out about absorption or distribution or metabolism or excretion or toxicity, or else everything together. So instead of only one property being predicted, you can predict the entire set of properties. So here you can see it has calculated all your properties. Some tests are still running, some are already computed. So we have to wait till all the computations are complete. So here you can see all tests, that is blue: absorption, distribution, metabolism, excretion parameters, and toxicity parameters. Here you can see the molecular properties. Okay, log P, rotatable bonds, acceptors, donors, total surface area. Okay, now you'll see that the surface area keeps on changing from tool to tool because these are prediction modules based on the prediction algorithm. The numbers keep on changing. Now here you can see solubility, K permeability, absorption quite high. Okay, then is it a substrate to glycoproteins? Yes and no and yes. Each of them indicate that the molecule has an ability to either the efflux or the removal of other compounds from the cell or itself also can be cleared out. Then you can look at the metabolism profile. You can see that certain enzymes are inhibited by this particular enzyme, which actually lands up into trouble. Okay, so toxicity parameters are still running. We'll not go into detail. One is the Ames toxicity. X toxicity is a standard test. Okay, whether it is involved in mutations. HERG1 and HERG2 tells whether the molecule can cause any problem with regards to. You can see still as having no here, but unfortunately this molecule does cause host problem. Then you can see whether it is hepatotoxic. Yes. You can see the doses are high compared to for toxicity. Okay, minnow and all are less. So this way you can run the second test on your compounds, which is called as PKCSM, after you execute for Swiss ADME. So any questions, students? So my screen is visible onto the presentation mode again. Okay, so from here we move on to the third tool, which is called as Protox 3.2, which is a useful tool again in the prediction of the toxicity of chemicals. So when you synthesize your compounds, before you synthesize your compound, please see to it your compounds are validated onto this all three these modules. So you can paste the canonical smiles of your compound. Okay, you can see that all the coxib has appeared. Then you can calculate different properties like organ toxicity which fall in this purview, like hepatotoxicity, neuro, nephro, respiratory, and cardio. Okay. Similarly, you can calculate all other plethora of targets which are supposed to can exhibit what is called as an off-target effect. So, if your molecule is targeting any of these in addition to painkiller, then they are off-target or can cause side effects. So, we will select all and we start the tox protection. So Protox has done its predictions, and you can see that it's Protox has done its prediction, and this compound buildings to toxicity 6. That means it's 6 and above toxicity. Okay, average similarity, there are 47 compounds similar whose predictions accuracy is around 50%. So remember, it's a 50% accuracy, but to your advantage, you can use it. Then all the starting physico-chemical statistics are given here. You can see the molecule. Okay, you can see all other properties, pointers, whether it is active, inactive, okay, toxic, non-toxic, everything is okay, and the probability associated with that. Okay, that means what are the chances that it is active or what are the chances that it is inactive. Everything is mentioned. Okay, which are the toxic targets? It shows that this molecule won't bind to any of these except for PGH1. If you can click on PGH1, you can find out what is PGH1. Okay, prostaglandin and how does it affect. All this is available in the network chart is available here. Okay, so this is basically the network pharmacology thing. So you can see that the active cluster it binds to these particular targets, whereas in active cluster you have got so many molecules in picture. Toxicity radar chart. Okay, so you can see that this molecule uh, probability of activity. You can see that there are a variety of activities this molecule can exhibit. Okay, so this way you can use the tools, computational tools at your disposal. Okay, to decide whether the compounds are okay available or not. Then next I will take you to the last part of my topic, that is ligand based drug design. Okay, so all we have seen is structure based where the protein comes in picture. So we've seen the structure based tools. We will go to the ligand based tools. So in ligand based tools, okay, you can have QSAR, what is quantitative structure activity relationship. Okay, this topic is vast by itself, but I will try to put it in words that if you have a set of compounds whose biology is available to you, it means MIC50, PIC50, all these values have been determined. Then what you could do is you can build what is called as a prediction model. Okay, and using this prediction model, you can, of course, you have to validate that model for accuracy and stability and rigidity. But however, after doing that, you can use this model to predict the activity of unknown compounds. Okay, so then the next one is pharmacophore. Okay, I will take a quick demonstration on this particular module. Okay, pharmacophore is basically an ensemble of features in the molecule which could be steric, electrostatic, okay, which are essential for an optimal interaction with the biological target, which results into a desired biological activity. Okay, now the features that form the part of a pharmacophore are referred to as pharmacophoric elements, and you can see the listed ones here. They have aromatic rings, okay, they could be hydrophobic structures, they could be cationic points, they could be anionic sites, there could be donor features, or there could be an acceptor feature. Okay, now okay, now how do we identify these features? Okay, now before we go to these features, we'll go into the two sites. Again, we'll go back to SwissDoc, but instead of SwissDoc, we'll go to what is called as Swiss Similarity. Okay, now sometimes when you do want to do a project, okay, find out chemical structures that you want to synthesize, or you wish they were similar in style. Okay, then you can use one tool which is called as Swiss similarity. Now the Swiss similarity, you can enter the molecule of your choice or a structure which you have identified and want to work around that particular molecule. Like again, I will pick up donepez. I'll pick up valdecoxib. Okay, this is a project that my students have performed. Okay, I will share the paper with you. So so what they did was they have chosen all the known inhibitors of COX-2, okay, and then they have tried to search databases, okay, like drug database, commercial database, synthesizable database, okay, and then based on the fingerprints. Now fingerprints are signatures unique to every compounds, okay. So a signature of two siblings, there's a possibility that two siblings may have a similar signature, hence we can say that the siblings are, they are related based on the similarity in the signature or some handwriting traces or something like that. So fingerprints in molecules also have fingerprints. So there are a variety of simplest is called as the fingerprint 2, and one higher one is called as the fingerprint 6. We use one standard one which is called as the extended connectivity fingerprints 4. Okay, there are various databases the computational fraternity and start screening. Okay, now this screening will help me identify compounds which are similar to valdecoxib. Okay, which I can then use in docking studies or any other toxicity studies and find out whether these are good molecules and go ahead with this particular compounds, either by synthesizing them directly or by buying it through the vendors. Okay, I can conduct a performer study. Now if I have to look at valdecoxib here, so I can see valdecoxib, or if I pick up celecoxib. So you can see a cox here. Okay, so I can see a lot of COX structures, okay, bound to different inhibitors. So I can see one here which is cyclooxygenase 1 in complex with celecoxib. Okay, now what I will do is I will download its structure, okay, in legendary PDB format. I downloaded that structure. So, so what I will do is I will open it in a text file. So what I will do is I will open this particular structure into text file. Must have opened here. Okay, then a little bit zoom it for clarity and go straight to the file where the inhibitor is launched. Inhibitor structure is available. So these are all water molecules in the PDB file. And this OG molecules. So I can see celecoxib cell here. So this is the celecoxib A. Okay. This is the molecule of my interest. I copy it in a new text file. Okay. So I save it as celecoxib. PDB onto my home folder. Okay, I try to reach to that molecule. You can see this molecule here. Okay, so I have celecoxib with me. I'll try to load it. The screen. I'll delete everything from the screen here and try to load the celecoxib structure. Okay, now to understand this pharmacophore, what I will see, you can see here is that there's a ring, three rings here. Okay, and there is a two donors here, and there is one acceptor, one donor. I can label these structures. Okay, I can label these atoms. Okay, and it will tell me the numbers of these atoms. So I can see here. So atom names I've posted. So if this is my aromatic ring, then I will define this particular aromatic ring with a centroid of these atoms. That is starting from 12, 13, 14, 15, 16, 17. So what I will try to do is I will try to open the file celecoxib, okay, and see where these atoms rest. So I can see that, okay, here see 15, 16, 17, 16, these are the center. Okay, so I what I want is I want a center, okay, which will be center of x comma center of y comma center of z for these. So I can use a quick reference from ChatGPT, or I can work them out manually. Okay, ChatGPT can give me two quick solutions. Okay, so we'll raise a hunt for calculate centroid from PDB coordinates of following atoms. So what will happen is I will quickly get the centroid of this ring, okay, which I now open a text file. I'll open a text file, okay, new one. Then okay, let me say put the centroid as C, okay, one C. Then I will put its coordinates. Okay, so these are its coordinates. Okay, I will paste it here. Okay, so I've got one centroid and I will save it as an XYZ format. Okay, so file, save. Okay, so this I will label it as pharmacophore, pharmacophore.xyz, and save it on my desktop. Okay, now if I load my pharmacophore file and this particular thing, see, the pharmacophore will get loaded. Pharmacophoric element will get loaded exactly in the center of this particular. Okay, so now I can define more pharmacophores like this. So I can define a pharmacophore for this. I can define a pharmacophore for this nitrogen, which is a acceptor. I can load pharmacophore this way. I can create pharmacophore for all of them. Okay, I can create pharmacophore for all of them. Now once I have these pharmacophore elements, okay, then I can go to a website called as a zinc farmer. Okay, I can go to a website called as zinc farmer. Okay, and okay, I can search the zinc database. Like in the earlier scenario, we have tried to search. Okay, of course, okay, we didn't go there, we didn't reach. It's still calculating, it's still running 79%. Okay, so here I can define the pharmacophore. Okay, so I can say add feature. Okay, so my feature was a ring, aromatic ring. Then I can use the coordinates of this aromatic ring to define this here like this. So what was the coordinates? So it was minus 32. Okay, so I can place the coordinates here. Okay, so that feature has got loaded. Okay, so once I load all these pharmacophore queries here, okay, then I can go and say submit query. Okay, so by submitting query, it will start searching. Okay, now what has happened is I've only posted one query because of the time constraint. Okay, so if I post all the queries here with their proper coordinates, like let's say if I put nitrogen and oxygen, I'll take another ring from this system and delete the hydrogens. Hydrogens are not a part of the exercise. Okay, then I can look into the score. I can pick this nitrogen as a uh, I can pick this nitrogen as a donor, sorry, an acceptor. So I search for N1. So N1 is here. So then I fix these coordinates as a add a feature. Then this feature becomes a acceptor. Okay, and then I paste this value here. Then get the second value. Third value. Okay, so this way I've got two features. I will add one more feature. Okay, that is this particular nitrogen, that is N3, which is a donor. You can see N3 here. So N3 is a donor. Add a feature, make it donor. So I should have at least three features to make my hypothesis, otherwise the rule of triangle does not work. Okay, so this way I will submit the query with three. So you can see it is searching around compounds, and you can see the compounds have come out. Okay, now there are a lot of hits in this range. Okay, so hits are going on high. Okay, I can filter these hits by giving, molecular weight ranges. I can put them from 300, I can put to 400, I can put rotatable bonds from 3 to 5. Okay, and then I can hits, I can put just 10. Okay, and then submit the query again. So what will happen is I'm tightening my constraints. Okay, so you can see only 10 hits have come out. Okay, I can save the results, it downloads it as an SDF file. Okay, and then I can load my SDF file into this viewer again to see the structures, or I can load the SDF file for docking again. Okay, so I can dock them again to see the query results here. So I can dock them to see whether the results are good. So now you can see here. Okay, so I wanted a donor and acceptor. So you can see. Okay. So you can see one structure come out in the same frame, but you can see that these two rings you can see for more structures. So you see more structures of similar site. Okay, you can see compounds matching in shape. Some of them not that great, some of them too high, too big. Okay, so this way we can do. Now these molecules again which you have identified from either from similarity search. I don't know if the similarity search is still running. Okay, so it is still running. It has got clogged or something. Some it has hit us. It has hit a bug. Okay, so it does not matter. So just like docking, it will give you results. Okay, so you can dock them, you can run your ADME tools, you can clean them up before you actually decide you want to synthesize them. Okay, or you want to buy them and directly test them. Okay, so this way I've shown you majority of the tools, okay, that are a part of computational chemistry, which are freely available. Okay, and uh, yeah, that's it. So, any questions from your end? I'll be happy to answer. Students, any questions?
Maybe no students have any questions, sir.
Any questions?
No, no, sir. Can we complete our lectures here,
Any
sir?
questions?
Sir, no one have any questions. Can we complete our lecture here?
Okay. So, can we conclude this session?
Yes, yes, of course, sir. Thank you so much, Dr. Raghuveer Pisulankar, sir, for that insightful lecture on computational approach towards drug discovery.
So, can
We
we
really
conclude this
appreciate you
session?
sharing your expertise with us today, and this session was incredibly helpful for our students. Thank you for your time and for inspiring us all. Thank you,
I
sir.
can't hear you.
Hello. Can you hear me, sir?
I'm not able to.
Hello. Can you hear me?
Hello.
Hello, sir.
Hello, sir. Yeah. Okay. I was not able to hear you. Okay. So, if any questions are there, then student can post it to you, and then we can send it across. Any questions or
Okay,
any
okay.
query? Or this chat box is there, right? That I can see comments coming.
Yes, yes, sir. I think no students have any
No
questions.
students have any questions. Okay. So we can conclude the session. Yes.
Yes, yes. Thank you so much, sir.
Thank you so much, sir.